So changes in mechanics can often signify the onset of disease. So the most commonly talked about example of this is the identification or palpation of lumps or tumours, commonly associated with cancer. But beyond just cancers, there's a whole host of other diseases where we see changes in mechanics, such as atherosclerosis, Alzheimer's, arthritis, and many, many more. So my PhD uses a technique called Brillouin microscopy, which seeks to find the mechanical properties or the micromechanical properties of our samples purely using light. So this is obviously really useful for biomedical diagnosis and applications where you want to limit the kind of poking and prodding and all of that as much as you can for a most comfortable experience for the patient. So Brillouin microscopy is an inelastic light scattering technique, and it essentially means that we shine a laser light at our sample and we collect back the scattered light. So the majority of the light that's scattered is elastically scattered. So that means that the frequency and the wavelength of our scattered light is exactly the same as the frequency and wavelength of the light that we sent in. So you can see this scattered light as the corners of the square in my PowerPoint slide. So we've got multiple squares here for a methanol sample. What we're really interested in are the yellow dots that are on the diagonals of these squares. So these are our inelastically scattered light, or our Brillouin scattered light, which occurs when the light enters the sample and it interacts with the sound waves that are inside that sample, intrinsically inside that sample. And the scattered light has a slightly different frequency to the light that we shone in. And so this change in frequency could be directly related to the mechanical properties of our sample. So what we're really interested in is understanding more about this technique. So it's fairly new to biomedical applications, and so we need to start somewhere simple. So we've started with simple gelatin hydrogels, which mimic biological tissues. Actual tissues are very complicated and complex, and so we want to start somewhere that we understand. So if you think about the jelly that you eat, very similar samples to what I'm using. So we start with something maybe soft like that. We can then change our concentration and get something a little bit stiffer, more like a gelatin cube that you dissolve to make your jelly. And finally, if we dehydrate our sample, we get something that's very stiff, like a hard-boiled sweet. So we get this whole range of mechanical properties just from this one sample. And because of this, we can really probe and understand what our Brillouin measurements are telling us, so that we can then use this to understand and use the technique for biological tissues and samples to understand in more detail things going on in disease.